half hours. Okay? All right. When we were last meeting together, we covered electrochemistry, and we said that the whole goal of the first half of chapter 19 was to be able to calculate redox reactions, and in particular, the goal is to balance. Okay? So when you get your final answer, your reaction should be balanced, which means that the number of electrons gained and lost should be the same. The number of individual atoms and elements, carbons, hydrogens, metals, whatever they are, should be the same on the left and on the right, in the products and in the reactants. Yes? All right. So when you get to the final answer, and it will be more tedious as we progress through it, always remember to check your final answer and ask yourself, are my atoms before and my atoms after all the same? Got it? All right. So let's look. And this is how a lot of the problems will be given to you as word problems. Okay? You will have to write the equation and then balance. So in a concentrated solution, and in all of these problems, when you see the word solution, you should assume it is an aqueous solution. Okay? So you have an aqueous concentrated solution. You're going to put in elemental zinc. It reduces nitrate ion to ammonium ion. Okay? So write the net ionic equation for this reaction. So zinc is reacting with what? Zinc is reacting with what? Okay, so zinc is elemental, so it should be solid. It is elemental. It is reacting with nitrate. What is nitrate? NO3 minus. Because it is an anion, it should be aqueous. The states do matter in this problem. Okay? It produces what? What does zinc become? Zinc. Yes, Xavier? Zinc 2 plus. Very good. And again, because it is an ion, it should also be aqueous. Okay? And what does it form? Nitrate becomes ammonium. What's ammonium? NH4 plus. And again, because it is a cation, it should be aqueous. Okay? Good? Next, what are we going to do? Before we balance anything, we need to figure out what? I heard it? Charges or oxidation states. Okay? So we need to, step one, assign oxidation numbers to each atom. And I emphasize the word each. Each atom. So that you know what is oxidized and what is reduced. So, under each, every single one, see, a lot of times I see you guys draw a circle under NO3. That's not each. Each means nitrogen gets a circle, oxygen gets a circle. Okay? Because they have individual oxidation states. Here, NH4, again, nitrogen needs an oxidation state, hydrogen needs an oxidation state. Then we apply our oxidation rules from last semester. When something is elemental, what is its oxidation state? Shimona? 0. Gave you an easy one. Oxygen, what is its oxidation state? Lexi? 2 what? 2 minus. Sorry, didn't mean to interrupt your panda eating. Because there are 3 of them, we need to multiply by 3 to account for the overall oxidation state of 6 minus. Now, we do need to find out what is the oxidation state for the nitrogen, But it does not equal 0. What does it equal? It must equal the minus charge here, so 1 minus. So what must be here to make this mathematical statement true? Must be 5 plus. Okay? There is only one nitrogen, so we don't really need to divide by anything because we're dividing by 1. Okay? So this becomes 5 plus. Zinc, that is 2 plus. What is its charge, Andrew? 2 plus. I gave you an easy one. Okay? Hydrogen, when bound to a non-metal like nitrogen, has a charge or oxidation state of what, Mercedes? Mercedes. Are you sure? Let's put up an example just to check. Since we think maybe it's 1 minus, maybe we think it's 1 plus, right? So let's take an example like NaH. Okay? Na is a metal, right? This is a metal. Okay? Na has what charge? Plus. So hydrogen must be minus. Okay? HCl is another one that we're very familiar with. Okay? This is a nonmetal. Do you agree? Okay. H is what? Cl is what charge? Minus. So H must be. So when bound to a nonmetal, must be 1 plus. It is good to remember these kinds of simple compounds that we learned in 151 to remind ourselves in case we forget the rule, right? All right. If it is 1 plus, and there are 4 of them, we have a 4 plus. And again, it must equal what? What is the overall charge is? Plus. So what must be here to make this true? 3 minus. And again, we only have 1 nitrogen, so it becomes 3 minus. Okay? I highly advise you do this step neatly and carefully, because here's the thing. You rush through this to do the next part. If these numbers are wrong, the whole thing is wrong. So you might as well just give up. Right? No, we're not going to give up. Okay? So make sure these numbers are correct. Otherwise, you're going to be hurting yourself down the line. Your answers, there's no way your answers will be correct. Now, the next step is to write one equation for the reduction and one equation for the oxidation. So you need 2 arrows, one for each. Okay? And we're going to look at what changes and what doesn't change. Okay? So should we write an equation for zinc? Yes, because zinc starts with 0 and ends up as 2 plus. Its oxidation state has obviously changed, so we're going to need to write one for zinc. And which side should we put the electron? On the right side. How many? For now, 2 plus, or 2 electrons. Because 2 plus, 2 minus should equal 0. All right. Has the nitrogen changed in oxidation state? It has indeed. So we're going to write not nitrogen, but the whole thing, NO3 minus. Okay? And to help ourselves keep track of things, I often will put on top here, very small, 5 plus. I've brought the number inside the circle down. Okay? Then I'm going to bring over my NH4 plus. And again, I'm looking at the N and saying this is 3 minus inside the circle. So I'm going to put a 3 minus here. Okay? The reason I do that is this will help me to very quickly figure out where the electrons go, right? If this is 5 plus and this is 3 minus, where should my electrons go? And how many should I need? Should need 8. And again, check your arithmetic. 8 minus 5 plus should equal 3 minus. Okay? Now, remember, the whole point is to do what? What's the word I'm looking for? Balance. I'm trying to balance. So is this balanced? This 8 and this 2? It is not. Okay? So therefore, I need to multiply this entire equation by what to make it 4. Very good. I'm glad you came back to us, Uriel. Okay? Now, you can either erase it or you can cross it out. It doesn't really matter. Okay? So now we are at this balanced situation. Okay? And what I like to do is I like to bring everything down. Okay? And remember, we can cross off these two because this is being used up, right? So this is being used up by this secondary reaction. Okay? So now let's bring everything down. 4 zincs. This is solid plus NO3. This is aqueous. It gives us 4 zinc 2 plus aqueous plus NH4. Again, this is aqueous. Okay? Last but not least, we should consider oxygen and hydrogen. Okay? Because the rules say for oxygen, you need to add water to balance and then balance the hydrogen with H+. We're in an acidic solution. Okay? So here on this side, I have how many oxygens? 3. So I need 3 oxygens on this side, right? So I write, very good, 3H2O. And H2O is always what state? Liquid. Okay? So how many hydrogens do I have on this side? I have 6 here. Then I have 4 here. So we have 10. So we need to write 10 H pluses. And again, it carries a charge, so it should be aqueous. Okay? And then you should check. Do I have 4 zincs? 4 zincs. 1 nitrogen, so on and so forth. Okay? Any questions? We good? All righty. We are good. No questions. You have a question? There are 3 oxygens here. Okay. There are 3 oxygens here. There are 6 plus 4. That's 10. So there are 10. It's okay. Your math is off today. It's okay. It's all right. Okay. All right. Example 19.1 from your book. It gives you the equation. So if you are following along and writing it out, okay, my advice is always don't squish your chemical equation so that you can't do the oxidation state. Spread it out nice and wide, right? Because you need to write circles under each element. So spread it out nice and wide. Don't be afraid to use paper. This is not the time to save trees. Not the time. Okay? You can save the trees some other time. Okay, and like I did before, I'm writing a circle under each element. All right, let's keep going. Okay, I2 is elemental. So what is the oxidation state, Uriel?
0.
It is 0. Okay. NO3, we just did this, right? 2 minus times 3 gives us 6 minus. We're going to bring down our overall charge of 1 minus to get 5 plus. Here we have, again, oxygen is 2 minus. We have 3 of them. So it is 6 minus. We're going to bring down our overall charge of -1. So we get, again, 5 plus. And last but not least, there are 2 of the oxygens. So we get 4 minus. Here, the overall charge is what? 0. It should equal 0. So the only way this is true is if this was 4 plus. Is everyone with me? All right. Now we're going to write our 2 arrows. One for the oxidation, one for the reduction. Has iodine, changed in oxidation state? It has indeed. But be careful. Okay? This is where a lot of people make mistakes. Okay? How many iodines are here? So ultimately, for it to be balanced, you need 2. Okay? That's something very, very important, because a lot of times we just zoom over. We're so busy balancing the charges and the oxidation states. So we are going to bring down the I2. Okay? But I would, for the sake of not forgetting, okay, write 2 iO3 minus, because you need 2 iodines. Okay? Now, when you're trying to balance the electrons, I always think one of them first and then multiply by however many you need. So a lot of times I will say, okay, I have 0 here. This iodine is 5 plus. So if it was 1 iodine, pretend, okay, if it was 1 iodine, you would have 5 electrons here. Do you agree? But do you have 5 iodines? Sorry, 1 iodine? You have 2 iodines. So really it should be 10 electrons. Did everyone follow that logic? Okay? If it was 1 iodine, you would need 5 plus. But because there are 2 iodines undergoing this process, you should have 10 electrons. Okay? What else is being changed? We're going to bring down our nitrogen, or actually the whole nitrate ion. Okay? And it becomes NO2 in this particular case. Okay? Now there's just 1 nitrogen and 1 nitrogen here, so that makes things simple. Okay? This nitrogen is 5 plus. This nitrogen is 4 plus. This math is super simple. So therefore you need 1 electron here. Okay. Then you're asking yourself, the goal of this is to balance. So 10 electrons, 1 electron, not balanced. However, what should we do? Multiply by 10. So we're going to go 10 and 10 and 10. Any questions? Okay. Let's bring everything down, canceling out our balanced electrons. Okay. So we're going to get I2. And now we're going to put in our states. I2 should be a solid. Okay. 10 NO3s, minuses, and again this should be aqueous. Okay. This gives us 2 iO3 minuses, should be aqueous, and 10 NO2, and this should be a gas. Last but not least, we are going to balance our oxygen and hydrogens. Okay? So oftentimes I like to keep track by writing it somewhere on the side. Okay? Because I, like the rest of you, are very bad at counting. Right? Okay. So how many oxygens here? How many? 30. How many oxygens there? There's 6 here. There's 20 here, so 26. Okay? So obviously that's not balanced. I need to add how many more on this side? 4. So let's add 4 waters to this side. That balances everything in terms of the oxygen count. And remember, H2O is always liquid. Then ask ourselves, on this side of the equation, are there any hydrogens? How about on that side? There's 8, right? So we should write 8 H pluses on this side. Again, it should be aqueous. Okay? And we are done. Okay? Both of these examples are redox reactions in acidic solution or acidic media. And we know this for a fact because there is H pluses always at the end floating around. Okay? Is that clear? Now, in this next problem, we're going to move on to something that's a redox reaction in a basic solution. Okay? So we should not end up with H pluses at the end. We should end up with OH minuses at the end. Okay? So really, you're going to do the same exact process that we've been doing. The only difference is in a basic solution, you're going to add 2 more steps. Okay? Step number 5, you're going to note down the number of H plus ions and add this number of OH minus ions to both sides of the equation, because H plus reacts with OH minus to form water. Then if you have waters on both sides, you should cancel them out so you only have waters on one side. Okay? Any questions? Yes, Xavier?
Will we always be told if it's going to be a basic solution as opposed to an acidic solution?
Yes, the problem will clearly indicate that this is in an acidic media or acidic solution or basic media. Okay? It'll be very, very clearly indicated. Okay? And truthfully, with these kinds of reactions, you're either doing this in an acid or a base. When you are setting it up, as a scientist, you should recognize that, oh, this is basic or this is acidic. Okay? All right, very good. So, let's do that example. MnO4 minus, and I'm going to drop my states and put it in at the very end. You can do the same on your homework just as long as you put them in at the very end. So what should I do right now? What is the first thing that pops into your head? We should be doing oxidation states with circles. Very good. Okay? So let's all take a moment and do it on our pieces of paper. Okay? Everyone do it. You need to be able to do this yourself. Okay? The oxidation states will not be given to you. Once you are done, please look up and check your answers and make sure that matches my numbers. You should get 7 plus, 2 minus, 4 plus, 2 minus, 4 plus, 2 minus, and 6 plus, 2 minus, unless I made a mistake. All right, what should we do next? Draw 2 arrows. We've got 2 half reactions. Very good. We're bringing down our MnO4, permanganate, and our manganese dioxide. All right. And again, we should bring down our numbers, our oxidation states, 7 plus and 4 plus. What is my next step, Matthew? So where do my electrons go in this particular case? How many on the left side? 3. Very good. Okay. Then we're going to bring down our SO3s and SO4s, our sulfites and our sulfates. And again, we should be looking at the oxidation states for the sulfurs. So say, Lily, what should I do next? Okay, I'm going to add 2 electrons to this side. Very good. What's next? Correct. Why do I need to multiply the top by 2 and the bottom by 3? Because we would like to balance our electrons. Very good. We like to balance. So we're going to multiply everything on the first half reaction by 2. So this becomes 6, 2, and 2. And everything by 3. This allows us to bring everything down. What is our next step? What should be our next step? Add waters because we need to balance the oxygens. All right? So again, we're going to, off on the side somewhere on a piece of paper, okay? Say, how many oxygens are here? 8 plus 9 is, I'm trusting your guys' math. What is, how many here? 4 plus 12 is 16. Again, I'm trusting you guys' math. Okay, so what do? Add water to this side, and we need to add 1 water because that will get us to 17. Very good. Okay, then how many hydrogens on this side? 2, so we're going to add 2 H pluses. Okay, but remember, we are in basic media. So we want to get rid of our H plus that we just added, okay, by adding OH minus on each side. So if I have 2 here, to get rid of it, I need to add 2 OH minuses, right? So I'm going to add 2 OH minuses, and I'm going to add 2 OH minuses here. Otherwise, the reaction would not be balanced. Okay? This becomes what? what does this become? It becomes 2 waters. Right? Yes or no? Yes, okay? But you've got a water over here. So you can get rid of one, right? So get rid of this water. And then you can change this to a 1. Okay? So your ultimate answer should be, I'm going to write it kind of small here, but I'm going to write it here. Your ultimate answer should be H2O liquid plus 2 MnO4 minus. This should be aqueous plus 3 SO3, 2 minuses, again aqueous, becomes 2 manganese oxides okay, and manganese oxide here should be a solid, okay, plus 3 sulfates and then you end up with your 2 hydroxides. And just like your H pluses, your hydroxides should be aqueous. Okay? Any questions? Okay? This written in black here is your final answer. Okay? You cannot stop at the blue. You need to go all the way to the black written equation. All right. Any questions? My advice is, if you get lost in the process, like it's not balancing out and you're just really struggling, don't try and erase and fix. Brand new piece of paper, start over from scratch. Because what if you made a mistake at the very, very beginning? Hard to catch that yourself, right? So brand new piece of paper, reassign oxidation states and see what went wrong. Okay? Otherwise, you can be very, very easily frustrated. So what I would suggest is, if you're doing it, you're spending 10 minutes and it's not working out at home when your homework, brand new sheet of paper, redo. Okay? This chapter, you should think, use as much paper as you need. Don't worry about saving the trees. Okay? All right. Next question. This is again in basic solution. Exercise 19.2 says H2O2, which is peroxide, is reacting with ClO2. It is forming ClO2 minus plus O2. Again, as before, we should assign oxidation states for every element. But this is tricky. Be careful. This is H2O2, which is hydrogen peroxide. It is one of those special rules, right? Peroxide is what? What is peroxide? O2, 2 minus. All right? So each each oxygen has a charge or oxidation state of what? Okay, if the overall charge of this is 2 minus, then times 2, it gets us 4 minus. Is that what we have? No. So it can't be 2 minus. It has to be what? 1 minus. So each oxygen in this case is 1 minus. I repeat again. Each oxygen is 1 minus. Okay? You will encounter things like Hg2, 2 plus on your homework. Okay? Again, each Hg is what? 1 plus. Otherwise, there's no way for you to get 2 plus as the overall charge. Keep this in mind, in the back of your mind when you're doing your homework. Okay? You got it? Okay. So where O2 is 1 minus times 2 gives us 2 minus. Overall charge is 0. What must be here to make this true? 2 plus. So be careful again here. Don't just bring the 2 plus up. Because there are how many hydrogens? So we're dividing by 2 to get 1 plus. Don't forget that. Okay? Then, again, this is very straightforward. 2 minus times 2 gives us 4 minus. It should be equal to 0. So this must be 4 plus. Be careful. The overall charge is 1 minus. So what number must be here? 3 plus. And again, oxygen is elemental. Okay. Again, we're going to draw our 2 arrows, one for each half reaction. For some reason, when I do redox reactions, my arrows get longer and longer. It doesn't need to be that long. So, what is being oxidized here? Be careful here. Oxygen is being oxidized, right? This is 1 minus. This is 0. These oxygens aren't being oxidized, but these 2 are. So we're going to write H2O2 on this side, and we're going to write O2 on this side. Okay? And again, be careful. It's not 1 oxygen, it's 2 oxygens. All right. So let's keep track here. This oxygen is 1 minus. This oxygen is 0. If you had 1 oxygen, where would you put the electron? You would put 1 electron here. But we have 2 oxygens, so we need to put 2 electrons here. Do we all follow that logic? Yes? Okay. Then, of course, the rest is very similar to what we did before. This Cl is 4 plus. This Cl is 3 plus. So again, we need 1 electron on this side. So this is your reduction. And again, we're going to balance. So we're going to do what to this 1 electron? Multiply that whole equation by 2. Okay. This allows us to cancel out our electrons and bring everything down. The next step is, of course, to do what? Count the oxygens. So again, off to the side, where I often like to do it, just do it in the margin of my paper. Okay? And basically, it helps me to count, because I'm bad at counting and remembering. Okay? So how many oxygens here? How many oxygens here? So 2 plus 4 is? So you guys are better at math than me. How many are here? And how many are here? So 6 and 6 by happenstance. Not always like this. How many hydrogens are here? So we need. And of course, this is a basic solution. So what are we going to do? We're going to add 2 hydroxides. And we're going to add 2 hydroxides to this side as well. just to keep everything balanced. This becomes 2 waters. So we're going to write 2 H2O. Cross this out. Okay. Then we're going to put in our states. Any questions? All right. This is the major part of electrochemistry. That's part 1, okay, on how to do redox reactions completely, okay. This is an extension of what we learned in 151, where we just did skeleton half reactions, right? Those seem so simple now compared to what we're doing now, okay? But really, just like before, it just requires a little bit of practice and you guys should be fine, okay? Calm, cool, and collected is my advice, okay? If you're trying to do this 10 minutes before it's due, you're going to be very stressed and then you're going to say, Dr. Chang is the worst. These problems are impossible to do. But if you go home this afternoon and just maybe some biscotti, right? Maybe tea is your preference, okay? And you just very carefully put in the oxidation states. Then very carefully bring down your half reactions. Then very, very carefully, maybe with a sip of coffee, count your oxygens, then your hydrogens. Then you'll be like, Dr. Chang, these problems are so easy, okay? So just remember, if you try and do these kinds of problems, these intricate problems with counting, and you're doing it in a rush, that's when frustration occurs. Okay? So just remember, a nice cup of cocoa, right? Maybe some marshmallows. Okay? You got it? Maybe some Costco pumpkin pie. Right? Okay? They are out this season. Okay? And then you just calm, cool, and collected, and everything will be fine. You got it? Any questions? All right, for your homework, let's pull out our homework booklets. Let's pull out our homework booklets. For your homework, we're going to start chapter 19. And most of you I saw did not start chapter 19 from last week. That's okay. Oh, do study for the exam. Wow, where's your chapter 19, Andrew? All right. We're starting from page 63. And we're going to do 63 through 66. Okay, all of those problems. Okay? Stop at the bottom of page 66. Okay? And like Xavier pointed out for us, make sure, read carefully. Does it say acidic solution or does it say basic solution? All right? We good? We feel good? All righty. Let's end class here. Okay, and I will see you next week. Do not forget, we do have a lab on Monday on Fischer esterification. The last lab, please do the pre-lab. Okay, please do the pre-lab. All right. Have a great rest of today. Good job.